exercise 3.8, graphing polynomial functions. If I've got a polynomial f of x and it's in this expanded general format, I need to be able to work with it to create a sketch. The first thing we do is take a look at the basic shape. If the highest power of x is even, so in this example here we've got to the power of 2 and to the power of 4, then what we're going to have is a parabolic appearance. We can either have a positive parabolic appearance or a negative parabolic appearance. If a, the coefficient of the highest term, is positive, then we're going to have a positive parabolic appearance. Now, when I'm saying parabolic appearance, what I'm meaning by that is that if we're coming from above, there'll be some stuff that goes on in the middle here, but we'll finish off going above as well. So you can see that the basic shape here is that we come from there and we leave up with some stuff happening in the middle here. We can also have negative parabolic appearance, and that is if we take a look at the a, the coefficient of the highest power, if that is in fact a negative number, then we're going to have this inverted parabolic appearance, as you can see there. As far as turning points are concerned, the maximum number of turning points that we can have is the highest power minus 1. So for this quartic, the highest number of turning points that we could possibly have would be 3. For the quadratic, the highest number of turning points we could have would be 1. So we've got parabolic appearance and we also have cubic appearance. And this is going to be for when we've got x to the power of 3. In theory, not that we have to work with it, but we could have x to the power of 5, x to the power of 7 as well. But positive cubic appearance, if the coefficient of the x cubed is positive, then we have something going up towards the right. And if it's less than 0, that is that it's negative, it goes down towards the right. So you can see those basic shapes. Now, as far as turning points are concerned, the maximum number of turning points that we can have for a cubic will be 2. That's just 1 taken away from the 3 there. So 3 minus 1 is 2. Therefore, the maximum number of turning points we can have is 2. Now, in some cases, we might only have 1 turning point, or just a point of inflection. But the maximum number of turning points is 2. So as said before, we can have a variety of turning points, and I've already explained that. Whenever we've got a function, so let's pretend this here is multiplied, okay? That should be in brackets at negative x, all right? It's not minus x, it's negative x. So we've got x minus 3 multiplied by 2 minus x multiplied by negative x multiplied by 4 minus x. When we have it in that factorized form, it's great for us to locate intercepts, but it makes it more difficult for us to work out whether it's going to be positive or negative. What we do is we take the coefficient of those x's. So this here would be just x multiplied by negative x multiplied by negative x multiplied by negative x. So if we did that, we're going to have x to the power of 4, and overall it's going to be negative because I've got a positive times a negative, which is negative, times it by a negative, which is positive, timesing that by a negative, which then makes it negative again. Finding the x and y intercepts, we do it in exactly the same way we've done in the past. X intercepts, we make y equals 0 and solve for x. For the y intercept, we make x equaling 0 and solve for y. We're also interested in repeated factors. So in factorized format, wherever we have repeated factors, then at, for example, x minus a, we're going to have a turning point at x equaling a that will be on the x-axis. So if it's an even number, that's what we're going to have. We're going to have a turning point. There'll be either a negative turning point or a positive turning point. If we have a repeated factor, again, x minus a, and it's to the odd power, then what we'll have there is a point of inflection. So a point of inflection basically means that we go up, we then flatten out, and then continue to go up again. If possible, we want to locate turning points. For quadratics, we know that turning points occur exactly halfway between the two x-intercepts, but that's not the case for quartics or cubics, so we can't assume that. Instead, what we do is use our CAS calculator. Later in the year, I'll teach you calculus, and there you'll be able to locate the exact locations of turning points using calculus. But for now, we'll have to use our CAS calculator to locate the turning points. So in this problem, what we need to do is sketch these following functions. And all of the above will make a lot more sense with the examples that I'll show you now. So I'll move on to those. Alright, so this is problem 1. We have to sketch this. Firstly, let's take a look at the basic shape. I've got x times x times x, so that gives me x cubed. So what we know is that it's going to be a positive cubic. We're going to start from here, something's going to happen, and then we're going to continue up. That's what the basic shape is going to look like. Because this is to the power of 3, the maximum number of turning points I could have here will be 2. Notice we're in factorized format, so this makes it really easy for us to work out the x-intercepts. So I make y equal to 0, and I solve for x to get -1, -5, and +2. And there's my intercepts listed. Y-intercept, just make x equaling 0, and that produces 0, -10. So what I can do is put in all those intercepts. I know that for my graph, it's got to go start from below, come up, and then it's also got to finish off traveling up because it's a positive cubic appearance. X-intercepts, I put those 3 in. Y-intercept, I put that in. Now, as far as the turning points are concerned, I'm going to use my CAS to work out where they are. But as far as my sketch is concerned, then it's quite easy. I know that I have to start from below, but then come through here, and then also somehow turn around and come back to this intercept. So clearly there must be a turning point in between here, and so I can position my turning point. Same thing down here, the graph is going down, cuts through the y-intercept, but then I need to be able to get back into this position. So there must be another turning point, and you can see where that is. So what do I do on my CAS? I put the function in, and then I go menu, analyze graph, and I'm after the max. I click on the left-hand side of it, then click to the right, and the turning point will be given. Do the same thing for the minimum, and I'll show you that now. So just using my CAS, first thing I'm going to define the function. So menu, actions, define. So there's f of x equaling x plus 1 multiplied by x plus 5 multiplied by x minus 2. So that's now defined. And of course, I can evaluate my y-intercept by just plugging in 0 for x. And I can also work out my x-intercepts by solving for f of x equaling 0. That is y equaling 0. Now these were easy to generate anyhow, but there's my x-intercepts. Now let's take a look at graphing f of x. Go to a new document. Sorry, I'll go to a new graph. Place in f of x. I'll just change my Windows settings. So I might, the x's are all good, but I might make -20. We might go as high as 30 here. Okay. So now to work out where the maximum is and also the minimum, I'm going to go menu, analyze graph. I'm going to select the maximum. So I'm just going to click over here on the left and then go over to the right. Not too sure what happened there. I'll do that again. Menu, analyze graph. I want the maximum. So to the left, and now to the right. So I've swept that across, and there is my maximum. And I'll do the same technique, but select minimum to get the other turning point. So from there, the way across, and there's my other turning point. So that's how to locate the turning points really easily. So for B here, I've got x minus 1 squared multiplied by 2 minus x. So the basic shape, I'm going to have x squared multiplied by a negative x to give me a negative cubic. So what's that going to look like? It's going to go down towards the right, something's going to happen, and then it's going to continue to go down towards the right. For my x-intercepts, let's just make y equaling 0, and so I'll end up with x equaling 1 or x equaling 2. Y-intercept, just plug in x equaling 0 to get y equaling 2 for that. Now I've got a repeated factor. Because I've got this x minus 1 squared, what I'm going to get at the position 1, 0 is either a maximum or a minimum. So it's going to be a turning point because it's an even power. But we're either going to have a minimum or we're going to have a maximum. And what I need to do is put in all the key information. So I've got 0, 2. The turning point is going to occur at 1, 0. Which kind of turning point, I'm not sure yet. We're going to cut through at 2, 0. And the basic shape needs to be coming down towards the right, something going on, then continuing on down towards the right. So when I look at that, the only kind of turning point I'm going to be able to have here, because the graph is coming from above and coming down, is going to be a minimum, like shown. Now, given I'm going to have that minimum, and given that I need to also come through to position 2, 0, then obviously there's going to be a maximum here. And of course, I can locate that maximum turning point by using my CAS, just like I did in A. For C, I've got 3 lots of x minus 2 cubed plus 3. This is very similar to quadratics that are in turning point form. Here it's a cubic, and then if you like, you can think of it as about being in a point of inflection kind of format. Now, the value outside the front of the function is positive 3. What are we going to have overall? It's going to be an x cubic that is positive, so therefore the graph is going to go up towards the right, something's going to happen, then continue on going up towards the right. For my x-intercepts, let's just make y equaling 0, and you can see that the x-intercept is at 1, 0. Y-intercept, sub in x equaling 0, produces 0, negative 21. And now let's take a look. Note that this format of the graph could be given as that positive cubic at the position 2, 3. So you probably guessed that already when I made the linking to it being similar to turning point form for a quadratic. So there's my 2 intercepts. That's where the point of inflection occurs, and the general shape going up towards the right. It flattens out at that point of inflection and then continues to come up positive. The next example is really interesting because what I've got is a repeated factor here to the power of 3 and then that linear x minus 4. If I look at the basic shape, then I'm going to have a positive quartic. So the graph's going to come down, something's going to occur, a maximum of 3 turning points, and then it's going to continue to go up positive again. X-intercept, let's make y equaling 0 and solve for x, and I get these 2 x-intercepts. Then my y-intercept, sub x equaling 0 to get that y-intercept. And now let's consider the repeated factor. I've got this to the power of 3, so I know it's going to be a point of inflection. It's either going to be a positive or a negative. All right, and there's nothing here I can tell. It's only going to be the creation of the graph that I can work that out. So at negative 2, 0, I'm either going to get a negative point of inflection or I'm going to get a positive point of inflection. Now, given that it's a positive quartic overall, then we're going to come down and then we're going to shoot back up. Here I cut through at 4, 0, so I can be either going up that way or down that way. I have to come through at 0, negative 32. So the only way of piecing all of that together is if this is a point of inflection, I'm going down towards the right here, then it must flatten out and continue on going down. There's no way I can draw it this way. So I'm selecting the negative point of inflection coming through there. It comes through here. Now I know that I need to come back into this for this x-intercept at 4, 0. So there must be a turning point there. So we come down, hit a turning point, and then go back up, and away we go. Notice that the location of this is just found using your CAS. E. What we have here is an x plus 3 squared and a 2x plus 1 squared. So there's two repeated factors here, a minus overall. General shape, we've got a negative squared multiplied by a positive squared to give us a negative cubic. So our shape is going to be happening like so. And there'll be a maximum of 3 turning points in here. X-intercepts, you can see they're given. Just making y equaling 0 and solving for x. The y-intercept, just subbing x equaling 0. And now, this is what's really interesting for us, is our repeated factors. So x plus 3, well, if we solve for x if we make it equal to 0 and solve for x, we're going to get negative 3. So that's logical. And it's to the power of 2. So that means it's going to be a max or a min. We're not sure. Same thing over here. At x equaling negative a half, we're going to get a max or a min. We don't know which one it is yet. We just have to look at the graph. So here's where it cuts through the x-axis. So I'm going to have a min, or I'm going to have a max. I'm going to have a min, or I'm going to have a max. Given that the overall shape is a negative quartic, it means it's going to come down from below here and then continue on going down after all the turning points have been taken care of. Now, what must occur is because I'm coming from this area, from below, then I must have a maximum there at negative 3, 0. And I must also have a maximum here at negative a half, 0. So I've got there and there. And then, of course, if that's coming through down, I must have a turning point in between here, which I do. And you can work out exactly where that is on your CAS. And then it comes through the intercept at the end. Problem 2. So here we've just got to use our CAS fully for these two. Notice that the algebra, when you start mucking around with these particular functions, is too difficult. So you won't be able to find the intercepts easily for any of these. So you have to use your CAS fully. I've already shown you how to do that previously, so you can see that video above. But basically, just define your function, put them in, work out your intercepts. You can see that in that previous little section on the CAS, and then the turning points I've shown you a couple of times now, how to get the max and how to get the min. So I won't waste your time and get you to see me do that again. You know exactly what to do. Here are the steps there for it.